Today, we're leaving the basics behind and making a massive jump. We're talking about the incredible engineering leap required to build utility-scale solar projects. If you've ever looked at a massive solar farm powering an entire city and thought, how does that actually work behind the scenes? Well, you're in the right place. We're going to break down the highly complex and honestly kind of invisible infrastructure that makes all of this possible. Here's our roadmap for this explainer. First, we'll talk about what stepping up to utility scale actually means. Then, we dive into the medium voltage backbone. After that, we'll break down a massive 60 megawatt PV project, and finally, a 20 megawatt hour battery storage system. Let's get right into it. Section 1, stepping up to utility scale. Because to really get this, we first need to define what leveling up actually means in the solar engineering world. So there's a very clear dividing line here. In level 1, you're dealing with commercial and industrial systems. The basics, rooftops, standard solar pumping, things like that. But level 2, that is utility scale, and it's a completely different ballgame. We're talking mega scale operations. You trade in your standard rooftop inverters for medium voltage networks, massive substations, and incredibly complex protection relays that have to comply with very strict international standards. At this mega scale level, you aren't just an electrician anymore. You're practically a power systems architect. You absolutely must master these medium voltage networks and substations because you are moving staggering amounts of raw energy. And doing that without frying the grid, or let's be real, frying yourself, requires some serious engineering chops. Which brings us to Section 2, the medium voltage backbone. In Chapter 4 of our source material, we uncovered this invisible infrastructure that handles all that raw power. And right at the heart of this Level 2 design is the RMU, or Ring Main Unit. If you're not familiar, this is a compact metal-enclosed switchgear that's insulated with SF6 gas. You can think of it as a heavy-duty traffic cop for medium voltage feeders. Its entire job is to connect, protect, and sectionalize. If something goes wrong out there, the RMU is literally your first line of defense. It isolates the fault and maintains loop continuity across these massive PV blocks so the whole plant doesn't go down. Let's track the actual journey of an electron through the system. It starts at the inverter, which outputs around 0.4 or 0.8 kilovolts. Then, boom, it hits the power transformer, which steps that voltage way up to 33 kilovolts. From there, it routes through the MV switchgear for fault protection before finally making its way out to the utility grid. This sequence right here is exactly how you take multi-megawatt power and push it efficiently over long distances. To really put this into perspective, just think about the sheer size of a 33 kilovolt switchgear next to a person. They are completely dwarfed. These aren't just your standard breaker boxes. These are massive, incredibly sophisticated units that detect short circuits or overloads to protect a multi-million-dollar plant. Plus, they integrate with remote SCADA systems so operators can monitor the whole shebang in real time. It's this wild fusion of heavy-duty machinery and smart digital control. Moving right along to Section 3, Project 1. This is a 60 megawatt peak PV plant because honestly, theory is great, but Chapter 5 takes us into the real world. I want you to just let this number sink in for a second. 96,786. That is the staggering number of individual Jinko solar modules required to build a utility-scale plant of this magnitude. Seriously, try to visualize nearly 100,000 panels, perfectly aligned, soaking up the sun. The physical footprint of a project like this is just immense. We're dealing with 60 megawatts of peak DC capacity, which translates to about 50.4 megawatts AC. All that power is flowing through 168 massive Huawei inverters and 6 individual transformer stations, and it's spread across roughly 287,000 square meters. To put that in perspective, that is way larger than most residential neighborhoods. And to safely manage and route every drop of that energy, the site relies on a heavy-duty 12-cell 33 kilovolt MV switchgear system. But here's the thing about utility-scale engineering. It's not just about cables and transformers. To truly operate at level 2, you have to master the financial models. You have to prove the investment is bankable. It's about outlining the actual economic reality of renewable energy at scale. Because at the end of the day, if you can't prove the math, the plant simply never gets built. And man, the math on this one is compelling. The total capital expenditure is a colossal 975 million Egyptian pounds, but look at the annual savings, roughly 214 million a year. That means this entire megaplant pays for itself in just 4.55 years. And over its 25-year lifespan, it's projected to generate a total return of over $5.1 billion. The main takeaway here is pretty clear. Rock-solid engineering directly drives massive financial success. Now, let's pivot to Section 4, Project 2, a 20 megawatt-hour battery energy storage system. Generating power is obviously crucial, but what happens when the grid you're feeding it into is unstable? That brings us to our second utility-scale challenge, stabilizing a weak power grid. And let's be clear, this is not just a backup battery for your house. We are talking about a massive containerized lithium-ion LFP system with a 20 megawatt-hour capacity. It uses an AC couple topology right at the 33 kilovolt point of common coupling. And what's truly amazing is its output capability. It can deploy 20 megawatts of active power support for 30 minutes straight, all while safely operating at a 92% depth of discharge. You can really think of this system as the grid's heavy-duty shock absorber. Whenever that massive PV plant we just talked about experiences a sudden drop in generation, say a giant cloud rolls over, or if the local grid suddenly gets weak and the voltage drops, this battery system instantly kicks in. It pumps out reactive and active power to balance the load and prevent a cascading grid failure. It is literally the ultimate stabilizer. But ultimately, this all comes back to building real-world competence. It's one thing to run the complex math for a 20 megawatt-hour battery in software like PVSys or ETAP. It is a completely different beast to actually get out there with hands-on grit in the field. Doing the wiring, handling the active battery assemblies, this is what bridges that critical gap between academic theory and actual boots-on-the-ground industry practice.